Welcome back to my class in Integral Calculus. For today, we will discuss the integrals of trigonometric functions. But before that, we will have a review of the derivatives of the 6 basic trigonometric functions and the trigonometric identities that will be useful when integrating functions involving trigonometric functions. Okay, we start with the derivatives of the 6 basic trigonometric functions. The derivative of sine is cosine. If the function y is sine x, the derivative of y is denoted by y prime. And the derivative of sine x with respect to x is cosine x. When the angle of sine is not a single variable x, when you get the derivative of sine, you multiply it by the derivative of the angle. Next, the derivative of cosine is negative sine. If the function y equals cosine x, the derivative of cosine x with respect to x denoted by y prime equals negative sine x. Next, the third of the 6 basic trigonometric function is tangent x. If y equals tangent x, the derivative of tangent is secant squared x. Again, if the function y is tangent x, the derivative of y denoted by y prime equals secant squared x. Number 4 is the reciprocal of sine, and the reciprocal of sine is cosecant. If the function y equals cosecant of x, then derivative of cosecant of x with respect to x is denoted by y prime equals negative cosecant of x cotangent x. The derivative of cosecant x is denoted by y prime and is equal to negative cosecant x cotangent x. Next is the reciprocal of cosine. The reciprocal of cosine is secant, and the derivative of secant is secant x tangent x. Y equals secant of x. Then y prime equals secant x tangent x. If y equals secant of x, then derivative of secant is denoted by y prime, and derivative of secant is secant x multiplied by tangent x. And last is the reciprocal of tangent. The reciprocal of tangent is cotangent. Y equals cotangent x. Then the derivative of cotangent is negative secant squared x. If y equals cotangent x, derivative of y denoted by y prime equals derivative of cotangent x is negative cosecant squared x. Please have these derivatives in your mind. Memorize them if you must, because you will find this useful when we integrate trigonometric functions. Now the integral of sine x with respect to x denoted by the integral of sine x with respect to x is equal to negative cosine x plus c. The integral of sine x with respect to x is equal to negative cosine x plus c, where c is a constant of integration. And this can easily be checked by getting the derivative of the right hand side. When you get the derivative of the right hand side, you should get the integrand sine x. The derivative of cosine x is negative sine x multiplied by negative is positive sine x. Plus derivative of any constant c is 0. Therefore, sine x plus 0 is sine x. Thus, the integral of sine x with respect to x equals negative cosine x plus c. Next, the integral of cosine x, denoted by this, the integral of cosine x with respect to x is sine x plus c. The integral of cosine x with respect to x is sine x plus a constant of integration c. Now the integral of tangent x, with respect to x, you can give the integral of tangent x in two ways. You can write negative ln of cosine x plus c, or so this is the first value of the integral of tangent x with respect to x, the negative of ln of cosine x plus c. Or you can write ln of secant of x plus c. The second value of the integral of tangent of x with respect to x, ln of secant x plus c, is used by many because there is no negative sign in the coefficient of ln of secant x. Next, the integral of secant squared. The integral of secant squared x with respect to x is equal to tangent x plus c. Next, we write the integral of cosecant squared x. The integral of cosecant squared x with respect to x is negative cotangent x plus c. In number 4, we have the integral of secant squared x with respect to x equals tangent x plus c. And the integral of cosecant squared x with respect to x equals negative cotangent x plus c. number 6, we have the integral of secant x tangent x with respect to x equals secant x plus c. And number 7, we have the integral of cosecant x cotangent x with respect to x. This equal to negative cosecant x plus c. And next, we have the integral of cotangent x. The integral of cotangent x with respect to x equals ln of sine x plus c. Now there are only two integrals left, the integral of secant and the integral of cosecant. And we write the number 9, the integral of secant x with respect to x equals ln of secant x plus tangent x plus c. And last, we have the integral of cosecant x with respect to x equals ln of cosecant x minus cotangent x plus c. Please memorize this, keep these integrals in your mind, because commit these integrals in your memory as well as these derivatives of trigonometric functions, so that it would be easier for you to integrate trigonometric functions. Next, we will have a review of the trigonometric identities that will be useful when simplifying integrals involving trigonometric functions. Some integrals that involve trigonometric functions are not readily integrable, but they can be simplified using trigonometric identities so that they may be reduced to integrals that can be integrated using one or more of these integration rules for integrals of trigonometric functions. Please memorize this or have them and keep them in your memory. Now we reviewed the trigonometric identities that will be useful in simplifying integrals involving trigonometric functions. The first is the set of Pythagorean identities. We have number 1, the sum of the squares of sine and cosine equals 1, or sine squared x plus cosine squared x equals 1. From this trigonometric identity, you can derive two more identities. If you transpose sine squared x to the right hand side, you will get cosine squared x equals 1 minus sine squared x. Or if you transpose cosine squared x to the right hand side of the equation, you will get sine squared x equals 1 minus cosine squared x. Now, the next is the reciprocal identity. Tangent is the reciprocal of cotangent. Tangent x equals 1 over cotangent x. Also, cotangent x is the reciprocal of tangent. And cosecant x is the reciprocal of sine. Secant x is the reciprocal of cosine. We have the following reciprocal relations. The reciprocal of tangent, denoted by 1 over tangent, is equal to cotangent x. Or cotangent x equals the reciprocal of tangent. The reciprocal of sine, denoted by 1 over sine, is the same as cosecant x. Or cosecant x equals the reciprocal of sine. The reciprocal of cosine, denoted by 1 over cosine, is equal to secant x. Or secant x equals the reciprocal of cosine, denoted by 1 over cosine. Next, we have the sine of twice an angles, sine 2x. The sine of twice an angle, denoted by sine 2x, where x is the angle. So 2x is twice an angle x. The sine of 2x is equal to 2 times sine x times cosine x. Now the cosine of twice an angle, with x as the angle, is denoted by cosine 2x. Cosine 2x is equivalent to 3 expressions involving trigonometric functions. Cosine 2x is equal to 2 times the square of cosine minus 1. 2 times the square of cosine x minus 1. And from this trigonometric identity, we can derive another identity for cosine squared x. By transposing negative 1 to the left hand side, becomes positive 1. And dividing both sides by 2. We write that the square of cosine x is equal to cosine 2x transpose negative 1 to the other side, becomes positive 1. And we divide both sides by 2. Another expression equal to cosine 2x is this. Cosine 2x is also equal to 1 minus twice of sine squared x, or cosine 2x equals 1 minus 2 multiplied by square of sine. And from this identity, we can derive an expression equal to sine squared x by transposing negative 2 to the other side and cosine 2x to the right hand side. We do that, we transpose 2 sine squared x to the left hand side. Sine squared x is equal to, we transpose this to the left, 1 is left at the right hand side, and transpose cosine 2x to the right hand side minus cosine 2x, and we divide both sides by 2, and we get sine squared x is equal to 1 minus cosine 2x to remove 2 here. We divide the left side, we divide both sides by 2. If we divide this by 2, 2 will cancel out from the coefficient of sine squared x, and we divide the right hand side by 2. This is the 10th identity. The square root of sine x is equal to 1 minus cosine 2x divided by 2. Now, another expression equal to cosine 2x is this, number 11. We have cosine 2x is equal to square root of cosine minus the square root of sine x. The cosine of twice an angle 2x is equal to square root of cosine x minus square root of sine x, or cosine 2x equals cosine squared x minus sine squared x. The next trigonometric identities can be obtained from this Pythagorean identity. If we divide both sides by sine squared x, we divide sine squared x by sine squared x, we get 1. Plus, we divide cosine squared x by sine squared x, we get the square root of cotangent. And we divide also 1 by sine squared x, and 1 over sine is cosecant x. Therefore, 1 over sine squared x is cosecant squared x. And from here, you can get another identity for cotangent squared x by transposing 1 to the right hand side, and you get cotangent squared x equals cosecant squared x minus 1. Again, from this identity, we divide both sides by cosine squared x. Divide sine squared x by cosine squared x, we get tangent squared x. Plus cosine squared x divided by cosine squared x is 1 equals 1. We divide by cosine squared x, and we simplify using this reciprocal identity or relation. 1 over cosine x is secant x. Therefore, 1 over cosine squared x is secant squared x. And please memorize or keep these trigonometric identities in your head or mind, because we will use them when integrating trigonometric functions. Now we will have examples for integrals of trigonometric functions. For our examples, we will evaluate the following integrals. To evaluate the integral is to find the derivative of the integrand with respect to the given variable. In number 1, we have the integral of cosine 3t with respect to dt. Number 1, we have the integral of cosine 3t with respect to the variable t. Now you can see that the angle of cosine is not an angle in one single variable. The variable t has coefficient of 3. We express this first as cosine of an angle consisting of a single variable. Thus, we let u be equal to 3t. Let u equals 3t. And we get the derivative of both sides. Derivative of u is 1 multiplied by du. Derivative of u. The derivative of 3t with respect to t is 3 multiplied by dt. Now, using u equals 3t, we will have a change of variable in the given integral, so that cosine will be a function of a single variable u with coefficient of 1. In the given integral, we will replace 3t with u, and we solve for dt from this equation by dividing both sides by 3. We have dt. You divide 3 dt by 3. And divide the left hand side by 3. And 3 will cancel out from here. You get dt equals du over 3. dt equals du over 3. Now, the given integral cosine of 3t with respect to t is now equal to the integral of cosine 3t is u and dt is du over 3. And one of the integration rules says that the integral of a constant times a function is equal to the constant times the integral of the function. 1 over 3 here is a constant, so we can take that out of the integral sign. We write integral of cosine u du over 3 equals 1/3 times the integral of cosine u du. Now you apply the integration rule for the integral of cosine function. The integral of cosine u is sine u. We have 1/3 times the integral of cosine u. Integral of cosine is sine. Sine u plus a constant of integration. In the final answer, we replace u with 3t to write the final answer in terms of the original variable t. Hence, the integral of cosine 3t with respect to t is equal to 1/3 times sine u equals 3t plus the constant of integration. This is the answer for number 1. The integral of cosine 3t with respect to t equals 1/3 times sine 3t plus c. We consider number 2. The given integral in number 2 is the integral of cotangent 5y and integrate with respect to y. As in example 1, we express cotangent as a function of a single variable. So we will have a change of variable for number 2 by letting u be equal to 5y. We have number 2, the integral of cotangent 5y with respect to y. We first let u be equal to 5y. Let u be equal to 5y and get the derivative of both sides. Derivative of u is 1 and multiply 1 by du. Derivative of 5y with respect to y is 5. And we differentiated with y. We indicate that by writing dy. In the given integral, we will replace 5y with u, and we solve for dy from this equation by dividing both sides by 5. 5 will cancel out from the right hand side. We get dy equals du over 5. Hence, the given integral of cotangent 5y with respect to y is now equal to the integral of cotangent 5y is, we let 5y be equal to u, multiply by dy, dy equals du over 5. And we apply the integration rule for the integral of a constant and a function. The integral of the product of a constant and a function equals the constant times the integral of the function. Hence, by that integration rule, we can bring 1 over 5 out of the integrand. In front of the integral sign, 1 over 5 times the integral of cotangent u with respect to u. Now we can apply the integration rule for cotangent of a function of a single variable. The integral of cotangent is ln of sine. Hence, the integral of cotangent u is ln of sine u. And this is now equal to 1 over 5 times ln of sine u plus a constant of integration c. And to write our answer in terms of the original variable y, we replace u with 5y. And our final answer now is 1 over 5 multiplied by ln of sine u equals 5y plus a constant of integration c. Thus, the integral of cotangent 5y with respect to y equals 1 over 5 multiplied by ln of sine 5y plus a constant of integration c. Now let us solve problem number 3. We are given the integral of 3 multiplied by cosecant 5x multiplied by cotangent 5x and integrate with respect to x. Again, you can see that the trigonometric functions cosecant and cotangent are not functions of a single variable with coefficient 1. But here the variable x has coefficient 5. So first we express the given integrand as cosine of an angle, single variable with coefficient 1. And we do that by letting u equals 5x. We let u equals 5x. And this implies the derivative of u is 1 multiplied by du. Du equals derivative of 5x is 5 multiplied by dx. In the given integral, we replace 5x with u and we solve for dx from du equals 5 dx by dividing both sides by 5. If we divide 5 dx by 5, we get dx. 5 will cancel out. We have dx. We divide 5 dx by 5, we get dx. We also divide du by 5, we get du over 5. Now we have 3 in the coefficient of cosecant 5x cotangent 5x. And you can bring this out of the integrand. You can write this in front of the integral sign. That's by property of the integration rule that says the integral of a product of a constant and a function equals the constant times the integral of the function. Hence, integral of 3 times cosecant 5x cotangent 5x with respect to x equals the integral of 3 cosecant 5x cotangent 5x with respect to x is equal to 3 times the integral of cosecant. We now replace 5x with u, cosecant u multiplied by cotangent. We also replace 5x with u multiplied by dx. We have shown dx is equal to du over 5. Again, we bring out 1 over 5 out of the integrand. And we multiply 1 over 5 by 3. We get 3 over 5 times the integral of cosecant u cotangent u with respect to u. Now, we can apply the integration rule for the integral of cosecant times cotangent, and the integral of cosecant times cotangent is negative cosecant. Is now equal to 3 over 5 multiplied by the integral of cosecant times cotangent is negative cosecant with respect to u, cosecant u plus c. Negative times 3 over 5 is negative 3 over 5 multiplied by cosecant. Our u is 5x plus the constant of integration c. Hence, the integral of 3 cosecant 5x cotangent 5x with respect to x is equal to negative 3 over 5 cosecant 5x plus c. Just remember that whenever the angle of the trigonometric function is not a single variable with coefficient of 1, you have to use this substitution to write the angle of the trigonometric functions as functions of a single variable with coefficient 1. Now we answer number 4. We are given the integral of the square of the sum of sine t and cosine t with respect to t. We have number 4, the integral of quantity sine t plus cosine t square with respect to t. The first step here is to write the expansion. This is a square. You write the expansion of the square of sine plus cosine t. This is actually the square of a sum, so you can make use of one of the special product rules which you must have taken from your algebra course. We write from your algebra the square of a sum or the square of a binomial is equal to the square of the first term plus twice the product of the two terms plus the square of the second term. In this special product rule, our A in the given integral is sine t and our B is cosine t. Hence, we write the expansion of sine t plus cosine t squared using this special product rule. Now, the integral of sine t plus cosine t squared with respect to t is now equal to the square of sine t sine squared t plus twice the product of sine t and cosine t. 2 times sine t, this is the integral of the square of sine plus cosine t with respect to t equals the integral of the square of sine t, sine squared t, plus twice the product of sine t and cosine t plus the square of cosine t, written cosine squared t, and we integrate with respect to t. Now we make use of a trigonometric identity, particularly the Pythagorean identity. Sine squared t plus cosine squared t is equal to 1. We write, but sine squared t plus cosine squared t is equal to 1. That's by Pythagorean identity. one of the trigonometric identities I have written earlier. Hence, this is now equal to the integral of sine squared t plus cosine squared t is equal to 1. 1 plus 2 sine t cosine t. 2 sine t cosine t with respect to t. Ina-apply one of the integration rules, the integration rule for the integral of a sum of two functions. It says the integral of sum of functions is equal to the sum of the integrals of the functions. Hence, the integral of 1 plus 2 sine t cosine t with respect to t is equal to the integral of 1 with respect to t. We write integral of 1 with respect to t plus the integral of this, the integral of 2 sine t cosine t with respect to t. And the integral of dt is t. 1 here can be written as t to the power 0, and you apply the power rule for integration where n equals 0, and we get t. For the second term, we take 2 out of the integral and we write plus 2 times the integral of sine t cosine t. In the second integral, we will make use of a substitution. You note that the derivative of sine t is cosine t. Or you may let u be equal to cosine t. The derivative of cosine t is negative sine t. But you will have negative here. Hence, it is better to let u. For the second term, we let u be equal to sine t, and we differentiate both sides. Derivative of u is 1 multiplied by du. The derivative of sine t is cosine t multiplied by dt. For the second term, we replace sine t with u, and the product cosine t dt, this product we replace with d. Hence, this is now equal to t plus 2 times the integral of sine t is u, cosine t times dt is equal to d. Now we integrate this by power rule where the exponent of u is 1. Hence, d is equal to t plus 2. The exponent of u here is 1. We add 1 is 2. And the sum 2 we use as divisor, divide by 2. Plus the constant of integration c. And 2 will cancel out. We get t plus the square of u. U is sine t. And the square of sine t we write sine squared t plus the constant of integration c. Thus, the integral of, in number 4, the integral of sine t plus cosine t squared with respect to t is equal to t plus the square of sine plus the constant of integration c. We now answer number 5. In number 5, we evaluate the integral of 5 times cosine squared 7x dx. Again, the angle here is not a single variable with coefficient of 1. The variable x has coefficient of 7. Hence, we will make use of a substitution by letting 7x be equal to u. We let u be equal to 7x. And this implies derivative of u is du, derivative of u is 1. Multiplied by du is du. Derivative of 7x with respect to x is 7. Multiplied by dx. And in the given integral, we replace 7x with u. We replace dx with du over 7. From here, divide both sides by 7. 7 dx divided by 7 is dx equals du divided by 7. Now the given integral is now equal to the coefficient 5 here can be taken out of the integrand. We write 5 before the integral sign by one of the integration rules. In particular, the integration rule for the integral of a constant times a function is equal to the constant 5 times the integral of this function, cosine squared. We replace 7x by u, and dx we replace with du over 7. Again, we can take out 1 over 7 out of the integrand and multiply it by 5. 5 multiplied by 1 over 7 is 5 over 7 times the integral of cosine squared u with respect to u. Now here we make use of another trigonometric identity to change this into an integral that can be readily integrable. We make use of this trigonometric identity for the cosine of twice an angle. The cosine in terms of, we write the angle in terms of u. The cosine of 2u is equal to 2 times square root of cosine u minus 1. This is the trigonometric identity for the cosine of twice an angle u. Cosine of 2u equals 2 times cosine squared u minus 1. And from here we solve for cosine squared u. We transpose negative 1 to the other side and we divide both sides by 2. We have 2 cosine squared u is equal to cosine 2u. Negative 1 transposed to the other side is plus 1. And we divide both sides by 2. 2 cosine squared u divided by 2. 2 will cancel out. And you get cosine squared u. We also divide the right hand side by 2. We get cosine 2u plus 1 divided by 2. Hence, we replace cosine squared u with cosine 2u plus 1 divided by 2. And this integral is now equal to 5 over 7 times the integral of cosine squared u is cosine 2u plus 1 all over 2. Integrate with respect to u. Again, we have 1/2. We have 2 in the denominator, or 1/2 is a constant, and we can take that out of the integrand and multiply it by 5 over 7. 5 over 7 multiplied by 1/2 is 5 over 14. Says that integral is now equal to 5 over 14 times the integral of cosine 2u plus 1 with respect to u. Cosine 2u plus 1 with respect to u. And we apply again the integration rule for the integral of a sum up to functions. The integral of a sum up to functions is equal to the sum of the integrals of the two functions. Hence, this is equal to 5 over 14 multiplied by the integral of cosine 2u with respect to u we have 5 over 14 multiplied by the integral of these two terms. We have 5 over 14 multiplied by the integral of cosine 2u plus the integral of 1 with respect to u. Again, for the integral of cosine 2u with respect to u, we will apply a change of variable because u has coefficient of 2 and the coefficient of the angle of cosine should be 1. For integral of cosine 2u with respect to u, we let w be equal to 2u. We differentiate both sides. Derivative of w is 1 times dw. The derivative of 2u is 2 multiplied by du. In the integral of cosine 2u du, we replace 2u with w. And we solve for du from this equation. We divide both sides by 2. 2 du divided by 2 is du. We also divide dw by 2. We get dw divided by 2 over 2. Now this integral is now equal to 5 over 14 multiplied by the integral of cosine 2u is w. Du is dw over 2. Plus the integral of 1 du or simply du. Again, 1/2 here is a constant and we can write it before the integral sign. We take 1/2 out of the integrand. We have 5 over 14 multiplied by 1/2 times the integral of cosine W with respect to W plus the integral of du is u plus a constant of integration. When we integrate cosine of W, we will add a constant. But that constant will combine to this constant and the sum is also a constant. So instead of doing that, we simply write the constant one time at the end. And we represent that constant by capital C, capital letter C. Now, cosine W with respect to W is now readily integrable using the integration rule for the integral of cosine. And the integral of cosine is sine. Hence, this is now equal to 5 over 14 multiplied by 1/2. Integral of cosine is sine. Our variable of integration is W. Plus, here we now replace u with the substitution we used earlier, u equals 7x. To write the answer in terms of the original variable of integration x, u equals 7x. Plus c. You may distribute 5 over 14, multiply each term by 5 over 14. Or we write 5 over 14 multiplied by 1/2 sine W is 2u plus 7x plus c. Or we have 5 over 14 multiplied by 1/2 times sine. We replace u with 7x. 2 times u. U is 7x. Multiplied by 2 is 14x. Sine of 14x plus 7x plus c. Again, you may distribute 5 over 14. Multiply each of these terms by 5 over 14. If you do that, the first term will be 5 over 14 times 1/2 is 5 over 28. Multiplied by sine of 14x. The second term will be 5 over 14 multiplied by 7x. 7 and over 14 can be simplified. And you get 5 over 2x. 5 over 14 times c. 5 over 14 is a constant times a constant c is a constant. And we still write that as c. Hence, the integral of 5 cosine squared 7x with respect to x equals 5 over 14 times quantity 1/2 sine 14x plus 7x plus c. Again, if the angle is not a single variable with coefficient of 1, make use of this substitution. And then in this example, we made use of this trigonometric identity for the cosine of twice an angle, from which we solve for the square of cosine. And here, after the substitution, we found that the first term involves a cosine of an angle that is not a single variable with coefficient of 1. So we made use of another substitution, W equals 2u. And in the final answer, the answer should be in terms of the original variable x. Now we will answer number 3. The integral of the square of the sum of 3 plus tangent y. For this integral, we again apply the special product rule for the square of a sum, or for the square of a binomial. In number 6, we have the integral of quantity 3 plus tangent y squared dy. To evaluate number 6, we have to first expand, write the expansion of the square of the sum of 3 and tangent y. And to write the expansion of the square of the sum of 3 and tangent y, we applied one of the special product rules, in particular the product rule for the square of a binomial, or the square of a sum. And from your course in algebra, the square of a sum, this is a binomial, the sum of two terms is equal to the square of the first term a plus twice the product of the two terms a and b plus the square of the second term. In number 6, 3 is a in the special product rule, and tangent y is b in the special product rule. Hence, the integral of 3 plus tangent y squared with respect to y is equal to the square of the first term 3, the square of 3 is 9, plus twice the product of the two terms, 2 times 3 times tangent y, plus the square of the second term. The square of tangent y is tangent squared y. And we integrate this with respect to y. We simplify. We have the integral of 9 plus 2 times 3 is 6 multiplied by tangent y plus the square of tangent y. We integrate with respect to y. Now we apply the integration rule for the integral of sum of two or more functions, that says the integral of sum of functions is equal to the sum of the integrals of the functions. Hence, the integral of 9 plus 6 tangent y plus tangent squared y with respect to y is equal to the integral of 9 with respect to y plus the integral of 6 tangent y with respect to y plus the integral of tangent squared y here plus the integral of tangent squared y with respect to y. Now we can take out 6 out of the integrand, and we write 6 in front of the integral sign. That's by using the integration rule for the integral of a product of a constant and a function. That says the integral of a constant and a function is equal to the constant times the integral of the function. Hence, the integral of 6 times the function tangent y with respect to y is equal to 6 times the integral of tangent y. And the same with the first integral, the integral of 9 dy, we take out 9 of the integrand and we write 9 in front of the integral sign. Hence, the integral of 9 dy equals 9 times the integral of dy. And the last term is plus tangent, the integral of tangent squared y with respect to y. The first two terms are readily integrable. We have the integration rule for the integral of tangent, and the integral of tangent is either negative ln of cosine, or the integral of tangent is equal to ln of secant y. However, the last integral of tangent squared y is not readily integrable, but we can write it in terms of an integral that can be integrated using a trigonometric identity. In particular, we make use of one of the Pythagorean identities that says the square of tangent plus 1 is equal to the square of secant. Here, the square of tangent y plus 1 equals square of secant y. But we have to solve for the square of tangent y from this trigonometric identity by transposing 1 to the other side. Hence, if we do that, we get the square of tangent y equals secant squared y. Transpose positive 1 to the other side, we have minus 1. And in the last integral, we replace tangent squared y with secant squared y minus 1. Now this is now equal to 9. 9 multiplied by the integral of dy is y plus 6 plus the integral of tangent y. I will use integral of tangent y equals ln of secant y. ln of secant y plus integral of tangent squared y using trigonometric identity is equal to secant squared y minus 1. Secant squared y minus 1 we integrate with respect to y. And this is equal to 9y plus 6 ln secant y for the third integral, for the last term, integral of secant squared y minus 1 with respect to y, we use the integration rule for the integral of difference of two functions that says the integral of the difference of two functions is equal to the difference of the integrals of the two functions. Hence, the integral of secant squared y minus 1 with respect to y equals integral of secant squared y with respect to y minus the integral of 1 with respect to y. And we have the integration rule for the integral of secant squared. The integral of secant squared is equal to tangent. And you must memorize the integration rules. We have 9y plus 6 ln of secant y plus the integral of secant squared y is with respect to y is tangent y minus the integral of 1 dy is y plus the constant of integration. Hence, the integral of the square of the sum 3 and tangent y with respect to y equals 9y plus 6 ln secant y plus tangent y minus y plus a constant of integration c. For our last example, consider the following. We are given the integral of the cube of sine x with respect to x. Obviously, this is not readily integrable, but if you can remember, we have an identity, trigonometric identity involving the square of sine. In particular, we have the Pythagorean identity that says the square of sine plus the square of cosine is equal to 1. We write sine squared x plus cosine squared x is equal to 1. This is the Pythagorean identity, and it says one of the Pythagorean identities. It says the square of sine plus the square of cosine is equal to 1. And from this Pythagorean identity, we solve for the square of sine by transposing cosine squared x to the right hand side. Hence, we get sine squared x, or the square of sine is equal to 1. We transpose cosine squared to the other side. We take the opposite sign of cosine squared, we get negative cosine squared x. The square root of sine x equals 1. Positive cosine squared x transposed to the other side, we get negative cosine squared x. And the given integral of sine cube x, integral of sine cube x dx we write as the integral of sine x times the square of sine with respect to x. Sine x times the square of sine is the same as sine cube x. The base is sine x. The exponent here is 2, the exponent here is 1, and the property of exponent says that if you are multiplying exponential notations with the same base, copy the common base and add the exponents. 2 plus 1 here is 3. And for sine squared x, we make use of this trigonometric identity. We get equals the integral of sine x multiplied by sine squared x is equal to 1 minus cosine squared x. We integrate with respect to x. Now we remove the grouping symbols. By distributive property of multiplication, we multiply each term of this binomial. We multiply 1 and negative cosine squared x by sine x. We get equals the integral of sine x multiplied by 1 is sine x minus sine x minus sine x multiplied by cosine squared x. We integrate with respect to x. Now we apply one of the integration rules. The integration rule for the integral of difference of two functions. That says the integral of the difference of two functions is equal to the difference of the integrals. Hence, the integral of sine x minus sine x cosine x squared with respect to x is equal to the integral of sine x, the integral of sine x with respect to x, minus the integral of sine x cosine squared x with respect to x. Now the first term, the integral of sine x with respect to x is readily integrable. The integration rule for the integral of sine x says that the integral of sine is negative cosine. But the second term, the integral of sine x cosine squared x with respect to x is not readily integrable. However, the derivative of cosine x is negative sine x, and we have negative sine x in the second term. Thus, we will have a change of variable for the second integral by letting u equals cosine x. we let u equals cosine x, and differentiate both sides. Derivative of u with respect to u is 1. Multiply by du, 1 times du is du. And the derivative of cosine is negative sine x multiplied by x equals the integral of sine is negative cosine x, and negative sine x dx, negative sine x dx is positive du. We write positive du times the integral plus the integral of cosine squared x. Cosine squared x is the same as the square of cosine x. Again, the cosine squared x is the same as the square of cosine x, but we let cosine x to be equal to u. Hence, the square of cosine x equal to cosine x squared is equal to u squared. And we integrate with respect to u. And this is now equal to negative cosine x. For the integral of u squared with respect to u, we apply the product rule for integration, where the exponent n is 2. And we integrate u squared with respect to u, we add 1 to the exponent, 2. 2 plus 1 is 3. We get u cubed, and the sum is used also as divisor. Divide by divide by 3 plus the constant of integration. And we write the final answer in terms of the original variable x. We replace u with cosine x. Replace u with cosine x equals negative cosine x plus the cube of cosine x over 3 plus c. Or this can be written as cosine x plus 1/3. Cosine x cubed is the same as cosine cube x plus c. The integral of sine cube x with respect to x is equal to cosine, this is negative cosine x plus 1/3 cosine cube x plus c, a constant of integration. For your practice, please try the following exercises. The instruction is to evaluate, that is, to find the integral of the given functions. In number 1, we have the integral of sine 5x with respect to x. You note that the angle, sine is a function of an angle whose coefficient is not a single variable, but has a coefficient of 5. So you will use a change of variable for number 1 by letting u equals 5x. The same with number 2, you will have a change. You will use a change of variable by letting u equals 7y to find the integral of tangent 7y with respect to y. Number 3, you are given that integral of 2 secant 3x tangent 3x. First, you will use a change of variable to convert this given integral as functions of secant and tangent of an angle whose coefficient is 1. In number 4, we have the integral of the square of sine minus cosine x. First, you expand this expression using a special product rule from your algebra for the square of a difference. In number 5, we have the square of sine 2x. Integral of 3 times sine squared 2x with respect to x. First, you make use of a change of variable by letting u equals 2x. And you will use a trigonometric identity for number 3. In number 4, in particular, the trigonometric identity that you will use for sine squared in number 5 is the one that involves the cosine of twice an angle. Cosine of twice an angle. In number 6, we have the integral of the square of cotangent x minus 1. First, you expand this expression using a special product rule from your algebra for the square of difference. And you will use a trigonometric identity for the square of cotangent. In particular, you use one of the Pythagorean identities. And lastly, you integrate the sine of x to the power 5 with respect to x. Here you write sine raised to 5x as the product of sine x and sine x to the power 4. And then you make use of Pythagorean identity for sine squared x. You will write this as sine x times sine raised to 4, and you write sine raised to 4 as sine squared raised to 2. Then you make use of trigonometric identity for sine squared. If you have a question about the lesson today, you ask your question in the comments below. And do not forget to subscribe to my YouTube channel, Art Kalisan. Thank you for being in my class today.